Welcome to another unit in business mathematics. This time I'm going to answer the question, what is a derivative, or rather, how can we use derivatives to actually get the slope of any type of function? Well, we can start with actually reminding ourselves that if we have a linear function, so more or less a line, we can take just any 2 points of this line and calculate the slope of this line, of this linear function. And this slope is always the same, so it's a constant slope. This, however, remains a problem if we have a function that is not linear, because in this case, the formula we use for calculating the slope of a function, when we have the 2 points x1, y1 and x2, y2, this term no longer is constant over all the points which are on the function. So what can we do instead? Well, we can calculate the tangent in our one point which we are particularly interested in. So if we want to calculate the slope in the point x0, y0, we calculate the tangent and the slope of the tangent. Tangent, that's the one function which just touches the function but does not intersect it. If it's a tangent, this means this line, this linear function, has the same slope as our function in the point where it touches the function. So how can we get this tangent? Well, let's first consider this function. Then what we do is we set any arbitrary point. That's the point up here. So in this case, the intersection down here describes x0, y0, or f of x0. And this point here is x1, y1. Then what we can do is calculate the slope of this line. However, this line is not a tangent. It intersects our function in 2 points. So what do? Well, we take this point and move this a bit closer to x0, y0. Like this. And again, we get our slope for this case. We see the slope of this line is a bit closer to the slope of our function here. So we do this yet once more. We see it's almost the same slope as here. So we move this increasingly closer and closer and closer until it's an infinitesimal distance to x0, y0. Then we actually get this tangent here, and this tangent has the same slope as this line. Mathematically speaking, what we're doing is we are taking the limit of x towards x0 and calculating here for this x, which is basically infinitesimally close to x0, and calculate the slope. And this is the slope of this tangent here. This expression, which is also called the differential quotient, that's what we call here the first derivative. And we mark this with this small mark here, or as we see later, there's also different alternatives on how to actually write down the first derivative. Let's have a short look at an example how this works in practical terms. That's again what I mentioned before as a determination or as a definition of the first derivative in a point x0. So let's consider this function x squared. If I insert this generally into my expression up here, I will get x0 squared minus x squared. So that was f of x0 divided by x0 minus x. If I take a closer look up here, I see this is actually the third binomial form. So I can split this up in this fashion. and then shorten these two parts. I'm left with x0 plus x. Now, without any problems, I can insert instead of x, x0, giving me as a result 2x0. And well, if you just recall what you know about this function, the first derivative of this function is 2x. So if we were to calculate the first derivative at the point x equal to x0, you would get 2x0. So this is the first derivative of this function at point x0. Well, that's already everything there is to answer this question we posed earlier on what is a derivative. So it's the slope of a function in any specific point, and we can get this via the differential quotient as given here. The only problem, it's pretty tedious work to always do this for every new function. And that's why in the next session we take a look which rules exist to actually make our determination of first derivatives a bit easier. Well, as I said, that's already all there is in this unit, so I hope you enjoyed it. I say goodbye and see you next time.